Hello, together in this video we will derive the Navier-Stokes equation. So to start deriving the Navier-Stokes equation, we must first define a volume of fluid. So here is a volume of fluid, V, which has a surface S. And what we are going to say about this volume of fluid is that V is just a fixed volume of fluid. We're not going to say anything else about it. And so to start with deriving the Navier-Stokes equation, we are going to start from first principles. That is to say, we're going to write down the Newton second law for the momentum density. So that's a quantity that I'll call pi, right? It's a vector. And it's equal to the density times the velocity u. Okay, so this second law writes in the following way. So first of all, we'll have the rate of change of momentum in v. So this is the rate of change with time, okay? That's going to be the first term of our equation. And the rate of change of momentum, or the momentum density in v with time, is going to be equal to the net inward flow of momentum through S. Okay, so whatever is in V is equal to, well, what is in V changes is equal to how much of it is going into V, so through S. And because this is Newton's second law, we need to add to this the net force acting on V. Okay, so this is Newton's second law for the momentum density, or at least as we have written it here, okay? So I'll define these three terms. There will be integrals over v or s, and so to simplify the notation, I'll write down that this first integral is capital I, capital 1 in Roman numerals. This is going to be 2, and this is going to be 3 like this. And I put a vector on it because we need to remember that these are vector quantities. And from now on, I'll try to explain what each of these terms are in terms of the variables, in terms of the quantities related to the fluid. So first of all, let's have a look at 1, okay? And 1 essentially is the rate of change with time of the momentum that is in V. So it's d by dt, rate of change with time, of the momentum density that is in V, so the momentum essentially. So this is going to be the integral over the volume of rho u, okay, times dv. So that is our first term. And so because we said that v was a fixed volume of fluid, then the integral and the derivative commute, and we can write down that this is the integral over the volume of d rho u by dt integrated over dv. And because it will be easier to continue the calculation using suffix notation, I'm just going to write down one term, one component of this term in suffix notation, and that component I'm going to write that it's 1i, like this, and that will be the integral over v, okay, of this, of d rho ui over dt, and this is integrated over dv. Okay, so this is our first term, right? It's the rate of change with time of momentum in v. Now let's have a look at the net inward flow of momentum through S. So that's term number 2. So 2 up. So 2 is going to be equal, so this is integrated over the surface. So I'm going to have an integral over the surface here, okay? And this integral is going to be the integral of how much momentum density goes through S. So that's going to be the momentum density, pi, okay, goes through S, so it goes with the velocity u across the normal to the surface. And I haven't defined this normal, but this n here would be the outward pointing normal. In fluid dynamics, it's quite customary to define normals as being outward pointing, okay? So in that case, whatever pi is coming in, if it goes along with the velocity, okay, and that the velocity is in the same direction as n, this thing is positive. But because n is outward pointing, that means effectively that things are coming out of v. Okay, that means that some momentum density is coming out of v. And so in terms, what that means is that 2 should be negative, right? So if the velocity is in the same direction as n, so coming out, we should have a negative rate of change of momentum in time. And so I need to add this minus sign here. If n was defined as being inward pointing, then we would not need this minus sign, okay? So this is the expression for our second term. So, okay, so this is the net inward flow of momentum through S. So that's our momentum, and it's flowing with the velocity through the surface of normal n, okay? So we need to integrate this over the surface. So if I want to write this using the velocity, then I get minus the integral over S of rho u dot n ds, okay? And it's actually easier to look at this expression in suffix notation. So for instance, if I write down a component, so that will be 2i, what I get is minus the integral over s of rho. Okay, now we think for a second. This dot product is between two vectors. So these vectors are, this is going to give us a scalar in the end. So the free index is this one. Okay, so that's going to be ui, and then this u will become uj nj ds. Okay, as simple as that. And from this, well, we can use the divergence theorem. Well, we see that there is n ds at the end, and we're integrating over surface. So we can use the divergence theorem. Which essentially gives us that this is equal to minus the integral. Now this time the integral becomes that over a volume. And we replace the nj ds by a divergence operator times dv. So what we'll have here is a divergence operator, which is going to be d by dxj. It's the jth index that is playing with our divergence here. And that's going to be rho ui uj. Okay? And this is to be integrated over the volume. Okay, so the third term in our equation 3 is the net force acting on V, and we can split up this net force acting on V into two categories. We can look at, first of all, the forces, the body forces. So I'm going to write down this first term as the body force, so integrated over the volume. Okay, so that's a force per unit volume. Also we can look at local forces, and these are going to be forces that are going to be acting on the surface, so that's going to be F local. And that's going to be integrated over S. So this is a force per unit surface. So we have these two categories, effectively, and let's just have a look at, for instance, the body forces. So F body can be, for instance, gravity. So we'll have rho g here. And we can also have other forces. I will not get into details of other forces that can get there. But I'll just keep rho g here in the derivation to keep track of what these body forces become and how we can essentially derive them in this equation. And for the local forces, effectively we will want to, they are integrated over a surface, and so to get an overall equation here that is involving integrals over a volume, what we will need to do is to be able to apply the divergence theorem. Remember, 1 is an integral over a volume, and 2 has become an integral over a volume via the application of the divergence theorem. This is an integral over a volume, and we need this to turn into an integral over a volume. So what we will want to do here is express f local in such a way that we can use the divergence theorem. And so what we'll do is I'm writing one index of it, f local sub I, here, okay? And I'm going to write it in a way that will allow me to use the divergence theorem later on. I'm going to write down nj tau ji, okay? And essentially here, this tau ji is an important quantity that is called the stress tensor. So the reason why I took nj tau ji instead of ni tau ij or ni tau ji is going to become apparent later. So for now, just bear with me. You could have also chosen a more ni, or for instance nj tau ij for that would also work, but you will figure out in the end that you will need to take a transpose of a matrix to make it work. So let's just take this for the moment, okay? Therefore, this term 3 will become the term in 3 integral over s of f local ds, okay? And if I take, so I can rewrite component. This will be sum over s of f local I ds. That quantity is going to be then written as the integral over s of n j, or rather I can write tau first if I wanted, tau j I n j ds. And what I see here is nj with ds and an integral over surface, so I can again apply the divergence theorem here. And the divergence theorem here give me that this is the integral over the volume of the divergence, which is on the index j, so that's going to be d by dxj of tau ji, and this is integrated over the volume. Okay, so this is my divergence theorem. Okay, and so that gives us this third term here. So we do have the first term here, which is the rate of change of momentum in v with time as an integral over volume. The second term, which is the net inward flow of momentum through s, which is this also volume integral, and the net forces acting on v involve one volume integral and a surface integral that we turned into a volume integral here, using the divergence theorem again. And so what we have here is essentially the whole equation turned into an integral over a volume. So I'll write down all the components. So the first term is integral over v of d rho ui over dt dv. That's my first term. And then it's equal to term number 2, which is minus the integral over the volume of d rho ui uj over dxj dv, plus the forces. The first force that we had was gravity, so that's this the mass there. The weight, sorry, so that's going to be the integral over the volume of rho gi dv, and then I've got this term due to the local forces involving my stress tensor, that's the integral over v of d tau ji over dxj, and this is over dv. So from there, what I can do is essentially bring everything to the left-hand side and within the same integral term. So I've got integral over v, and that's going to be d rho ui over dt. Then this becomes a plus, so I've got plus d rho ui uj over dxj. And these become minuses, so I've got minus rho gi minus d tau ji over dxj. The whole of this equation being integrated over v, and this is equal to 0. This is a component. I've written this equation in component form here by taking the little i's in there, here for instance, there and there. So there is no need for vector here. This is a scalar. Alright? We didn't say anything about this fixed volume of fluid, so it can be as small as we want, and it can be as small as a fluid particle or as a blob of fluid, where therefore this is going to be locally valid. So because we can let V be as small as a fluid particle, and I'm not talking about a particle in the chemistry sense, but I'm talking about, you know, a small element, an elementary element of fluid. And in this context, then this equation becomes valid locally, so it's d rho ui over dt plus d rho ui uj over dxj minus rho gi minus d tau ji over dxj equals 0. And I can write it in a slightly different way, just to make the equation a little bit nicer to look at, by sending these two terms onto the right hand side, and essentially that gives me d rho ui over dt plus d rho ui uj over dxj, and on the right hand side I get rho gi plus d tau ji over dxj. To simplify this equation, we must first remember mass conservation, and so if I write down the mass conservation equation in component form in index notation, then I can write d rho over dt plus d rho uj over dxj equals 0. Or in other words, I can also multiply all this by ui and get that it's ui d rho by dt plus ui d rho uj by dxj equals 0. And what you should see here, what you should recognize here, is that these two terms, they're a subset of the terms that are going to come out of this left-hand side here. Okay? And therefore, these two terms are equal to 0, so I can simplify this equation by taking out these two terms of these, this left-hand side. What I get out of this is a simplified equation where if I take out the u here, the ui here, d rho dt, so effectively what I get is rho dui by dt. And similarly here, taking out the ui is part of this equality, which is then equal to 0. So what I get here is plus rho uj dui over dxj. And this is equal to the same right-hand side, rho gi plus d tau ji over dxj. Okay, this is our right hand side. So we've written down this equation here. So this is called the momentum transport equation for a fluid. This is written here in index notation, and if you want to come back to vectorial notation, we can do that and write down that this is rho du vectorially by dt, plus here we see a dot product between u and nabla. So this is going to be rho u dot nabla u. This is equal to rho g. And what we see here is that d by dxj, and j is the first index of the stress tensor, and therefore we have a divergence here. This is the divergence of the stress tensor, tau, this way. And so this is the momentum transport equation. Okay? So what we have here is the divergence of tau. Notice if I get back here, if I had written tau ij, I would have carried over here with tau ij, and I would have d tau ij over dxj, which means that I would have had to write here the divergence of the transpose of the stress tensor. That would have just made the notation a little bit more complicated, and therefore that's the reason why we typically write the stress tensor, we typically define the stress tensor in this fashion. So based on this equation, and to continue deriving the Navier-Stokes equation, we need to understand, we need to define our stress tensor. So we are going to do this now. First of all, we'll take the example of an ideal fluid. And in an ideal fluid, well, the local forces, the forces acting on the boundary, there is only one of them, and it's the force due to pressure. So F local will be equal to the pressure, and the pressure acts in the normal direction, inwards, always in this fashion. And so the density of force is going to be equal to minus P times N, right? So we can write that in a different way, in component notation, by writing the definition of F local, which, let me remind you, is Nj tau Ji. This is going to be equal to minus P Ni, right? And from this we can deduce that tau Ji equals minus P delta Ij, where delta is the Kronecker operator. Okay, so the pressure only acts in the normal direction and in the direction normal, right? To the fluid particle. That is to say, it's only providing normal stresses. And so this gives us the momentum transport. So the momentum transport for an ideal fluid then becomes rho dui over dt plus rho uj dui over dxj equals rho gi plus the divergence of the stress tensor, that is to say, plus d minus p delta ij over dxj. Okay? These terms remain the same, I will not change them, so that's rho dui over dt plus rho uj dui over dxj equals rho gi. And effectively what this is doing is saying that that delta is 1 only if I equals j. So this is going to be non-zero if only in the case it is dxi at the bottom here. So what we have here is minus, so this is a minus sign, dp over dxi, right? And we still have I as our free index everywhere here. In other words, what we have here, if you want to turn this equation if you write down this equation in vectorial form, we have rho du over dt plus rho u dot nabla u equals rho g minus the gradient of the pressure. And this equation is known as the Euler equation. So this is the equation of motion for an ideal fluid. Now that we've seen what the equation of motion for an ideal fluid is, let's turn to Newtonian fluids. So Newtonian fluids, they behave pretty much the same as ideal fluid, except that they also present some friction between different fluid particles. So the difference is that there will be compared to ideal fluids, Newtonian fluids are characterized by friction, also known as dissipation or viscous effects. What is it? Is nothing else than adding to our stress tensor. So we had our stress tensor written up. So tau ij, and that was minus the pressure on the diagonal. Okay, so minus the pressure times the Kronecker delta, ij. And what we're going to do is to this just add a viscous stress tensor. So that was the stress tensor, okay, stress tensor, or total stress tensor, depending on how you want to call this. And this is going to be called the viscous stress tensor. Okay, and the deformation, well, and these this viscous stress is going to be due to the deformations of the fluid. Okay, so sigma, the tensor sigma, is going to be proportional to the strain rate tensor, because friction is due to to the ability of the fluid to deformate. Okay? Ability of the fluid for deformation. So, and the idea here is that we will write sigma ij as a coefficient times the terms that are used in the strain rate tensor. So this is the strain rate tensor. So that was the symmetric tensor associated with the velocity gradient. So this is going to be dui over dxj plus duj over dxi. Okay. In other words, this is twice times mu times eij. Now the 2 comes here because the definition of eij was to be the symmetric tensor associated with a gradient of velocity, and therefore we had to put in 1/2, hence getting this 2 here. And this coefficient, which essentially gives up the law for the fluid, for the Newtonian fluid, how much it reacts, how much force is acting on this fluid due to gradients of velocity. So this coefficient is called the dynamic viscosity. And it's called dynamic because it's related to forces. We're looking at the forces acting on the fluid. It's from the Greek dynamis. Okay? And so once I've got this written down, I'm going to take this expression for the stress tensor, for the viscous stress tensor. The momentum transport can simplify. So if I write down my momentum transport, then I get rho dui over dt plus rho uj dui over dxj equals rho gi minus dp over dxi, and then there is these terms that come in, so I've got plus mu d by dxj, that's the divergence of our stress tensor. So d by dxj of dui by dxj plus duj over dxi. Okay? And we're fortunate because these terms effectively will simplify, so I can continue writing my momentum transport equation here and write down that it's rho dui over dt plus rho uj dui over dxj equals rho gi minus dp over dxi plus mu, that first term here is d2ui over dxj squared, okay? And the second term is mu d2ui, sorry, uj, d2uj over dxi dxj, okay? And what is important to notice here is that this term involves the incompressibility condition. So for an incompressible flow, so so the divergence of the velocity, so dui over dxi equals 0. Okay, so duj over dxj equals 0. I could put a j here to get closer to this expression, and therefore what I have is that d2uj over dxi dxj equals 0. What that means is that my momentum equation for a Newtonian fluid writes rho dui over dt plus rho uj dui over dxj equals rho gi minus dp over dxj dxi plus mu d2ui over dxj squared, and that term has disappeared. And so if we want to write that in a vectorial form, we can, and that writes in this fashion. So this is rho du over dt plus rho u dot grad u equals rho g minus the gradient of the pressure, and what we have here is a Laplacian, so that's going to be plus mu times the Laplacian of the velocity. Okay, and this equation is the equation that is known as the Navier-Stokes equation. Alright, so in this video we've derived together the Navier-Stokes equation. This is an equation that is widely used in fluid dynamics that we will see in other videos.